second part of our course on answering linear queries, which I understand will be split between Sasho and Gerome, who also goes by Sasha.
Sasha G.
Yeah, Sasha, I don't know. So we'll pick up where we left off.
Yeah.
Get away.
Thank you. All right, so I ended on this note that we have this matrix mechanism, which in some sense is the best you can do if you have a very large database. But when you have a small database, there are better things you can do. In particular, if your database is very small, you see if you do something like just add Gaussian noise with some distribution, if your database really is like very small, has like 1 or 2 rows, you may be able to just do better by like outputting something without even looking at the database. It should be clear that for very small databases, you can have sort of less error. But of course, we'll talk about smarter mechanisms which kind of try to stay closer to the optimal error, or at least get reasonable error in this regime of like small databases. Okay, so start with one method which is still kind of feels like kind of data independent, but starts to get some data dependence and to do better things for small databases, which is the projection mechanism. So let's remember some things. We were encoding our database as this histogram, and we were saying, which just gives us for every possible database type how many rows of that type there are in the database. And we observed that if you add up all the coordinates of this vector, which is what its L1 norm is, if you add up the coordinates of this histogram, you just get n. So okay, so if the database has size at most n, then this like sum of the coordinates of the histogram is at most n. So, and we said, given a query matrix, the vector of query answers is just the product of this query matrix and the histogram. Okay, and H is a vector of L1 norm at most 1. And this, remember, is my notation for all vectors of L1 norm at most 1. So you have that this vector of query answers has to be in the image of the set of all vectors with this L1 norm multiplied by W, right? But remember, okay, so this set of all vectors of L1 norm at most n, is just n times the, it's just the set of all vectors with L1 norm at most 1 multiplied by n, okay? And I can always pull out the n in front, right? And remember, this is just what I call my sensitivity polytope. So in other words, I have this set which contains all possible query answers on databases of size at most n. This is the set, and it just turns out to be exactly n times the sensitivity polytope. But think of this as just the set of all possible query answers on databases of size at most n. Okay, so I know that my true query answers lie somewhere here. And if I just add like data, or like, right, if I just add data independent noise, like say just run the Gaussian noise mechanism, I'll compute the true query answers and add some Gaussian noise. If n is very, very small, then the set of possible query answers is also small. And it could be that this is so much Gaussian noise that I'm very likely to get outside of this set. And I get a vector of like noisy query answers, which could not have, which is not in the set of possible actual query answers, right? So at this point, it's very natural to, even just to make the queries more, like the query answers more understandable, it's very natural to project back into this feasible set of possible query answers. It's a very natural thing to do. And this is what the projection mechanism does. And this is from, again, this paper with Kunal and Li Zhang. The projection mechanism is just run the regular Gaussian noise mechanism to get your noisy query answers, and then find the closest point inside this set of possible query answers. We'll do this in Euclidean norm, in like L2 norm. Find the closest point inside the set of possible query answers to the noisy query answers. Okay, so if the Gaussian noise didn't get you outside of this set, you just stay there, or you just output that. But if it took you outside, you project back to the closest point that's actually feasible, that could have actually come, like, could have actually been an answer to these queries. And this is the point that you output. This is the output of the projection mechanism. Good. And the point is that we already achieved privacy by adding the Gaussian noise, and then we don't touch the data again in this mechanism. So this projection is just post-processing. It's a very natural post-processing. So it does not affect privacy because differential privacy is robust to post-processing. OK. So what's surprising maybe is that this projection is not just kind of a sensible thing to do, and maybe it makes the query answers easier to explain, but it also could reduce error, at least in certain parameter regimes. So I initially was thinking of showing this proof, but I realized maybe this would be a little too many inequalities on the board. I really like this proof, but anyways, I will not end up showing it. So using a little bit of high school geometry, basically, like just geometry with triangles, and a little bit of probability, you can show that the mean squared error, so far we were talking mostly about worst case error, but remember there was this notion of mean squared error where I took the squared errors and I averaged them over the different queries. So the mean squared error you can show is bounded by square root of the database size. Remember, these are unnormalized counting queries. By the square root of the database size times this power of the log of the universe size. Okay, and this is actually a relatively easy proof, kind of using this observation that if you look at this triangle, these are the true query answers, these are the noisy query answers, and this is the projection. It must be that this angle is right or obtuse. And you work with that a little bit, and eventually with some work you can derive that. Yes?
Is it the squared error or the error? L2 error. So the square root of n log to the fourth?
So this is the square root of the mean squared error.
It was defined as the root mean squared error.
Ah, I see.
The root mean squared error, I should have said. I tried to make everything on the same scale. So this is on average how much error, think of this as the average error. This is on average how much error you get per query. Yeah, I was taking the square root. Okay, and there are some things for which this is optimal, even for this root of the mean squared error. Again, another result of John, Mark Bunn, and Saluvodan is that this is optimal even for mean squared error or root of mean squared error for two-way marginals. Again, this was our example where we saw that the matrix mechanism doesn't do always as well as we would hope, but then you can do this. So you can do some simple post-processing and even just on top of the Gaussian mechanism and do quite well. Okay, and again, the projection does not affect privacy, but it could improve the error bounds if your database is small, because that's exactly the case where the Gaussian noise takes you outside and then you go back in, and that can actually sometimes improve the error bounds. Not, and it never makes the error worse is maybe something that's important to say. So the error never becomes worse and can sometimes improve a lot. And the other thing I want to say is this post-processing sort of turns a data-independent mechanism, it was just the Gaussian noise mechanism, to something that sort of is data-dependent, because if I start from here, add noise and project, this will be a different distribution than if I start from there, add noise and project. Yes?
Sorry, Sasho, I don't remember what the relationship between n and d was when you talked earlier about small n. So what do you mean by small n?
Definitely the data-independent methods, like just add noise with some distribution methods, they seem to be close to optimal when you have more data than the number of, much more data than the number of queries.
Sure.
Let's say number of queries over epsilon.
Right.
Here, this actually kicks in and starts to be better, maybe even earlier than that, but okay. So, for particular queries, these data-dependent things could be better even for larger n. I mean, what am I actually saying? Let me think about it.
So when n is less than square root of the number of queries divided by log this thing,
right?
The projection is better. This technique is better.
Like in general, the data independent things do quite well when n is at least number of queries over epsilon. Let me just say that. Okay. And okay. I guess they could still be competitive even for smaller n, but in general they're not. I mean like the data independent things. But yeah, I think the rule of thumb is more data than queries. Okay. Good. Let me, I think this is important to say. So let me talk a little bit about something that's important that I haven't been talking about at all. So far I've been assuming that all these counting queries are just given by their truth table. So I've just, for every counting query, really listed for every possible row in the database, what is the value of the query. But of course, often in practice, the queries are specified in some implicit way that you don't just list all their values from the whole universe. You have something like R-way marginals. We saw 1- and 2-way marginals. I think you can now infer what like 3- and 4-way marginals are. I'm not going to define it explicitly because I don't use them. But you have things like this that are like very compactly specified. You can imagine a query specified by like a little circuit, for example, or like a little formula, or like some compact expression. And then in those cases, you would definitely, also because usually the universe is huge, you would want to have algorithms that achieve the same kind of error bounds that I've been talking about, but in much faster time. And going back to this seminal paper of Cynthia Moninor, Omer Reingold, Guy Rothblum, and Salil Vadan, we know that in general, getting non-trivial error bounds in time that's sublinear in the size of the universe is computationally hard under some reasonable complexity theory assumptions. Right? So if I just hand you a circuit that specifies like a bunch of circuits that specify the queries, then doing anything non-trivial in time much faster than this could be computationally hard. But they show this for relatively artificial families of queries. If you have like very natural specific families of queries, like 2-way marginals, 3-way marginals, we still don't really know what we can do in time that's polynomial in the dimension of the data, rather than the universe size, which is more like 2 to the d, and say the database size. Okay, and for 2-way marginals, in fact, we could have a more efficient algorithm using the projection mechanism. So let me talk about this a little bit. So again, projection mechanism, you just add Gaussian noise project onto the set of feasible query answers. So clearly adding Gaussian noise is not the expensive step. This you can do very efficiently. The expensive step is projecting. And with a little bit of work using sort of known results in optimization, you can reduce projecting on the set of feasible query answers to solving linear optimization problems over the sensitivity polytope. Okay, so if you can solve this linear optimization problem for an arbitrary linear objective, where the feasible set is the sensitivity polytope, then you can also project. You can do this using the Frank-Wolf algorithm and other methods as well. However, you can think, what is the sensitivity polytope for 2-way marginals? It's not very hard to describe kind of theoretically. And then you can think, what does it mean to solve these sorts of optimization problems over the sensitivity polytope for 2-way marginals? And you realize that you can encode max cut this way. Okay, so you realize this is an NP-hard problem. Okay, so that sort of seems like a no-go. But the simple idea is not to project on the sensitivity polytope, but project on some larger set on which we can project efficiently. Okay, so in this paper with Cynthia and Kunal, we show that you can come up with sort of a relaxation L of the sensitivity polytope. Relaxation because it strictly contains it, but it's not much larger. So it's contained in just a constant times the original sensitivity polytope. So it's like almost the same size, but using a semi-definite program, you can actually project efficiently, meaning in time polynomial in the dimension of the data on L, on this relaxation L. Okay, so this is sort of a cartoon of what this looks like. And this way, because L is only slightly larger than the sensitivity polytope, you get essentially the same results as the projection mechanism for the actual sensitivity polytope, but you get them efficiently. As in, again, polynomial time in the dimension of the data. Yes, so, Adam, you seem confused.
No, what you said was clear. So I had a question about what hardness for max cut, say, really implies here. Does it imply that, I mean, obviously it implies it's hard to do this projection exactly.
Yes.
Does it imply, do hardness approximation results for max cut tell you you can't get close to the polytope? Is there like, or do notions of approximation translate naturally here? Or?
I would have to think more about that. I'm not sure.
Yeah, so I think this order 1 in this inequality
It seems
It's like the
by
Gomez-Williamson.
1 over the Gomez-Williamson constant.
yeah. Except we sort of we do some other things, and it's more like the Grothendieck constant. But yeah, kind of roughly the Gomez-Williamson constant. Yeah, those do seem related, I think. So like finding this relaxation definitely is essentially the same as like finding a good efficient relaxation of the max cut problem. But just what this hardness means and hardness of approximation.
I guess where I was going with this is sort of, is there any reason to think that in practice it's actually hard to get onto the to do the projection?
So I think you can do things like in dual vector, you can use some solvers and just hope it works well. And I think that seems very reasonable. I should say, at least in theory, so in practice, then you can hope to do that also for three-way marginals with some solvers. But in theory, we don't know an algorithm which is efficient in terms of dependence on dimension and does this kind of thing for three-way marginals. We don't know how to like write these semi-definite programs. This is sort of, and there's like some evidence that the usual ways to do that don't work. So this is a frustrating challenge that I think like many of us have struggled with. Okay, I will, I think, skip this so that I don't cut too much into. Sorry, Thomas, if he's here, so that I don't cut too much into Jerome's time, and he say something else. So I talked about this projection mechanism, but it was just post-processing on top of the Gaussian noise mechanism. But we also talked about other ways to add noise that's independent of the data, which was the matrix mechanism. So you could try to combine the two. You could try to both do this factoring of the queries into reconstruction and strategy queries, answer the strategy queries, reconstruct, and then project onto the set of feasible answers. This is a very reasonable thing to combine both of these. And now, of course, the question would be, how do you find the right factorization? And you would want to, take some upper bound on how well noise plus projection does and minimize that. And you can try to go through all of this. I won't do this in as much detail as I did it for the matrix mechanism. But you can, and this is another result from the same paper, and I have some improvements in a later paper. You can show that doing these sorts of things with some caveats that the projection actually is a little bit different from what I described. You can show that you get a mechanism whose error is like close to the optimal error for every n and for every set of queries. But close to the optimal is up to these factors which are logarithmic in n, which I think is not so horrible, but also logarithmic in the size of the universe. And the size of the universe is usually enormous. It's usually kind of exponential in the natural dimension of the data. So this is a factor which is more like the dimension of the data. So it looks good when you put it there with a log. If you're like a theory person, you think logs are good things. But it's really a log of an exponential thing. So it's not as great as it could be. And it's open to not have this log of universe size there. And I should say this is only for sort of this root of mean squared error. We don't have similar results for worst case error. And I think that's also a nice theoretical open problem. Okay, so now let me finish with sorry, a little late, right? Let me finish, with the final class of algorithms, which are really kind of data dependent and take a different viewpoint, which is more like the viewpoint of trying to learn the database as you're answering, or in order to answer your counting queries. So the things we saw so far, especially in the morning, were sort of tools to answer sort of a small number of queries on a large database. Okay, there we saw that this data independent noise works well. So one idea would be, can you, given a large workload of queries, can you try to reduce answering all of them to answering a few of them, can you try to answer a few of these queries and generalize from there to all the rest of the queries? And I think this viewpoint maybe can be traced back, at least implicitly, to this very seminal work of Blum, Liggett, and Roth. Okay, at least sort of this viewpoint. So let me introduce some notation, which I hope is not too confusing. So the way I think about this is like, for these algorithms, you can think of the database as actually being a function that assigns to every query its value. Okay, it's like just a notational difference, really, like or a syntactic difference. But I think it's helpful to think of the database this way as a function from queries to query answers that you're trying to learn. Okay, so I'll have this notation, which is, I'm just switching what is inside the parentheses, what is outside. So, but all I'm saying is think of the database as a function that assigns to the query its answer. Okay, and now the goal would be to sort of take a few examples of queries and answers. Really, those would have to be noisy. And from those few examples, learn the entire function that maps, all the queries to their answers, approximately. Okay, so way number one to do this is based on boosting. So let's say you have some mechanism with good mean squared error guarantee. So let's say the root of the mean squared error is eta, so the average of the squared errors is bounded by eta squared. Let's say you have a mechanism like that, and I'll try to get from there to having small error on all the queries. So this is the kind of thing that with projection we can do well even on like many queries. Okay, and you first can observe that just sort of by Markov or Markov's or Chebyshev's inequality, knowing that the average squared error is small means that for most of the queries the error is small. So say with these numbers I can say that for all but 1/4 of the queries the error is bounded by twice this eta. In other words, what I have is that I can approximate the query answers. I can approximate this like function with this database function which maps queries to query answers on most of the queries. I know what it has on most of the queries. So in some sense, I have like weakly learned this function. And I want to strongly learn this function that is learned on all of the queries. And here, so this is very non-technical, right? On a very high level, this sort of reduction of strong learning to weak learning was done by Freund and Shapiri back in the 90s, who designed this sort of framework of boosting, which allows you very generically to give strong learners based on having weak learners for some concept class that you're trying to learn. And there is a version of this due to Cynthia, Guy Rothblum, and Salil Vadan, which is private boosting, which kind of similarly reduces worst case error to mean squared error. So using private boosting, you can run a base mechanism with good mean squared error a relatively small number of times, and from that extract a mechanism with good worst case error. Okay, and you can apply this, for example, to this projection-based mechanism for two-way marginals, and also get sort of optimal or essentially optimal worst case error, even in I talked about how do you get very good mean squared error. Turns out that mean squared error is also like close to optimal, and using boosting you can also get good worst case error. Again, quite close to optimal. And all of this is efficient. If the base algorithm is efficient, then the boosted algorithm is essentially as efficient as well. Okay. So this is learning approach number one. Learning approach number two is just a recap from Rachel's talk yesterday afternoon. So this is the private multiplicative voice mechanism. So the viewpoint here is that we're going to view the database maybe less as a function, more as a probability distribution that we're trying to learn. So the observation is just, if I look at this histogram and I divide every entry by n, then I just get a probability distribution on the universe. And this probability distribution is just for every universe element x, every possible database row, what is the fraction of the database that is equal to this database row. So this is just the empirical distribution of the database. Okay, so like a normalized histogram. And we said before that the counting query answers are given by this product of the query matrix and the histogram. If I divide everything by n, this is the same as the query matrix times the normalized histogram. So these are just the normalized query answers. These are just normalized counting queries where instead of asking how many rows in the database satisfy a predicate, I'm asking what fraction of the rows in the database satisfy a predicate. And for these normalized queries, if I get error alpha, this is the same as getting error alpha n for the unnormalized queries. Okay, and for like any probability vector p, any like kind of possible normalized histogram, I'll use this notation Q of p for basically just the coordinate of this matrix vector product that corresponds to Q. And this is really just, let me pretend that p is the normalized histogram, what would be the normalized counting query answer. Okay, and you can see because p represents x, we'll try to learn p in order to answer the queries that we care about. And this is really a recap of yesterday. So this is the private multiplicative weights mechanism. I think what Rachel described was closer to what was actually here in this paper by Hart and Rothblum, which was an online mechanism. I'll describe sort of the offline version of it, which is in a slightly later paper. It's a little simpler to analyze, I think. Right, so the strategy will be we'll like try to keep guessing what the correct distribution is. We'll start from some uninformed guess, which is the uniform distribution over the universe. And we'll try to keep improving this guess as long as we're making a mistake somewhere. If we're not making a mistake, then we are done. So this will proceed in rounds. In every round, I'll try to privately find the query so that the true query answer and the query answer given by my current guess is wrong by more than alpha. If I cannot find one, then I'm done. Then my current guess for the distribution is clearly good enough for all the queries that I care about, so I can stop. But if I do find a query on which I'm doing badly, then I just update my guess of the correct distribution in some way that allows me to like say that I'm making progress, that I've learned from my mistake and I can improve my guess. Okay, so this query is what I'll call the distinguisher between the true normalized histogram and our current guess. And you can find a distinguishing query just by just running the exponential mechanism with the score, which is just the error. So this is just the true query answer. This is the thing that's sensitive minus the thing that's given by my current guess in absolute value. So this is just the error that I'm making on this query. And I choose one query with this score function. And you can see the sensitivity is 1 over n here because the sensitivity of this normalized query answer is 1 over n. And that determines the sensitivity of the score. And the update rule is this multiplicative weights update rule, where intuitively what's happening is the following. So let's just take one case of this where, let's say the current guess overshoots, so it's like too large. Then the sign of the difference between the true answer and the current guess is negative. So what I'm doing is I'm taking the probability of any element of the universe that contributes to the query, and I'm decreasing this probability by a multiplicative factor, and then I'm renormalizing so that I have a probability distribution again. Okay, so if my current guess is too large, then I look at all the things that contribute to the query and I just decrease those probabilities, and I'll do the opposite thing if I make an error in the other direction. And like a very brief sketch of why this works. So the claim is that you can answer these the normalized queries with error alpha, which is the same as the unnormalized queries with error alpha n, as long as n is at least this big, which translates to the same kind of error bound that we've seen before, but in the worst case. So the error is on the order of like square root of n times square root of log k times this fourth power of log of the universe size. And roughly how this is shown is you use a potential function, which is the relative entropy between the true distribution and your guess. Okay, this is what relative entropy is. It's also known as scale divergence. Initially, our initial guess is the uniform distribution. So this is an initially log of universe size and is always non-negative. Those are just facts about relative entropy. And we can show that every update, with the update we chose, decreases the relative entropy by at least alpha squared over 4. So you can do at most this many updates. So this is a bound on the number of times we need to run the exponential mechanism. And this is really the only way we're touching the data, is running the exponential mechanism. And from this, a standard analysis of exponential mechanism plus advanced composition, you can derive this error bound. And this is, I guess, an exercise. OK, and I'll stop here. Here are a bunch of things I didn't cover. Yesterday, we heard some talks from Sasho and Rachel about synthetic data. You can use private multiplicative ways to get synthetic data. There are other ways as well. I didn't talk much about that. It's very interesting to answer sort of adaptively posed queries online. The private multiplicative weights mechanism can be adapted to do that. But sort of this rich theory of like achieving optimal error in different regimes, there is not much of that known. And there are also other methods to answer like implicitly defined queries efficiently. Some very interesting work. This is just one example paper. There are a few more based on low-degree polynomial approximations of this function that we're trying to learn. I didn't talk about lower bounds much. I'm sorry, John. And I didn't talk much about applied work, but we'll hear more from Gerome about that. And we'll stop here.
While Gerome sets up.
The bullet you had about replacing the exponential mechanism with above threshold.
Yes.
Did you say what you meant by that?
I didn't really.
Could you give one?
I was just saying I presented this version of private multiplicative weights where you use the exponential mechanism. And I was saying if you want to make it online, you can use above threshold.
You mean if the difference is above threshold? Or?
Right. This what I'm calling the above threshold mechanism. I think this is what you called it in the book.
No.
No? Am I confused?
One's above threshold, yeah. Okay. And then the
But I
sparse vector is what I thought.
sparse vector. Let's call it sparse vector. Yes, sparse vector.
Sasho, while Gerome is
Yes.
setting up the kind of the algorithms you mentioned, where you for conjunctions where you approximate things by a polynomial, can they also be viewed as some sort of matrix-like, matrix mechanism-like thing, but done at some implicit level? Is that the right way to think about it?
I think you can view them as.
John says yes.
I say yes.
I think so. Yeah. It's like I guess it is like approximating the query matrix with a smaller matrix, right?
Yeah, it's
some
like
sense.
it's like a low rank approximation to the query matrix.
Is it, like everything is sort of still linear in the right way?
Okay.
Everything
is linear in the right way.
I think so. Yes.
Yes.
All right. So, do you want to introduce Gerome?
So we have Gerome Miklau from UMass Amherst, who's done a lot of great sort of theoretical and applied work on this topic, and is going to give, maybe since Sasho presented like the theoretical view on the matrix mechanism, I assume Gerome will present like the applied view on Sasho's mechanism.
Something like that. Thank you. Yeah, and Ryan McKenna's going to help out in the middle. So I'm going to focus on the same task that Sasha focused on. Batch, sometimes known as non-interactive query answering, of a workload of linear counting queries. And as he told you, linear counting queries are good for lots of things. And I want to take a moment to sort of address where the workload might come from. And because I view this as part of a desirable interface for a differentially private mechanism, that a user or stakeholder, somebody who's studying the data, will express their needs and preferences through choosing a workload. And it may be that they have a more complex data analysis task in mind, maybe fitting a model, but they can decompose that into a set of sufficient statistics that are linear counting queries. It could be that a set of multiple users are bound to a single privacy budget, and so they have to sort of they're each interested in slightly different things or maybe overlapping things, and they put it all together into a workload. Or you may not know exactly what you want to know, and we know that we can't preserve accuracy for everything, so it's okay if we overestimate what we're interested in a little bit and put that in as the workload. And we'd like to have mechanisms that do the hard work for us, given a user who's expressed that workload. Okay, so what I'm going to try to talk about is more applied and informal view of the algorithm landscape. And there will be a little bit of review here, but I think it'll be useful to see some of the data agnostic and matrix mechanism type techniques from a different perspective. Then and the data dependent mechanisms. Then I'll talk about a use case from the census, which is kind of a live use case based on work that we're doing with the census. And that would be a good time to break if I can get through that stuff. It's a suspenseful moment because I'll ask a rhetorical question, and then Ryan will help answer the rhetorical question, and then we'll see what happens on the census workload and come back to adaptive algorithms and some more empirical results. Okay, so here's, so I'm going to present two approaches, and this is sort of just a different view of stuff that Sasho has said, that there are these data agnostic mechanisms, and that almost all of them fit a certain form. So now, like if we just invoke the Laplace or Gaussian mechanism, we could take our workload and we could certainly answer it, and we get workload answers with noise. And one of the motivations that started our work on this was that one byproduct here is that these query answers are inconsistent. So you can get results like the number of people under 30 plus the number of people over 30 is not equal to the noisy estimate of the total number of your population. Okay, and this is distressing for people who look at the results. So consistency was one of our motivations. But in addition, if you have the workload composed in the way I described on the next slide, the workload could be high sensitivity, there could be a lot of noise, and you'd like to find something to do that's better. So these data agnostic mechanisms, a lot of them what they do, and as we learned in the matrix mechanism, they interpose a separate set of measurements. They invoke the Gaussian or Laplace mechanism on those, and then you have noisy measurements, but not the noisy measurements you want. So you need to get estimates to the workload queries, and you'd like those to be consistent. Okay, so we'll call this, another name for this is sort of like the select, measure, and reconstruct paradigm. I'll refer to it that way. You don't necessarily have to solve a hard optimization problem to select measurements. Maybe you just have insight into your workload. For example, we learned that the threshold queries, which we call the prefix queries, are a nice set of measurements for those are this hierarchical tree thing. Okay, and then we'll reconstruct them. Now, one thing that didn't arise in Sasho's presentation is that when we were doing this, and a lot of the empirical work, there's a principle here by which we chose to reconstruct. There's obviously more than one way to take these noisy measurements and to reconstruct answers to the workload queries. And our way of doing it was sort of like minimizing the squared error between, using these as evidence and deriving the H histogram that is sort of like, that minimizes the squared error given your evidence. Okay, and then once you have the H histogram, which we're going to call X. So now if we were good tutorial designers, we would have like unified all of the notation and everything. And we didn't do that because it's sort of an experiential thing. This is what it's like to be split between the theory and applied worlds, where the variable names don't line up. H becomes X, little n becomes big N, and yeah.
Sorry, this is like a longer answer. You can feel free to punt it off. But why is the thing you described not like exactly the projection mechanism Sasho described, like finding the closest set of answers given the measurements?
No, are you reconstructing the vector of outputs or the actual?
I think it's because we're fixing a reconstruction. I think we talked about this a little bit. I think it's because we're fixing a reconstruction method. And at least in our...
I think Adam answered that. Reconstructing the histogram versus reconstructing the query answers.
But also my projection uses the fact that you know a bound in the database size. That I think can matter.
Okay.
So
one is projecting on a subspace, and the other is which is easy, and the other is projecting on this convex hull, this polytope, which could be hard.
Another question in the back, yeah?
Just for the use case that you specified, in the census context, a workload that you try to then reconcile across different results, right, so that they add up. Would that be within one of the queries or across multiple ones in time? Like
that would be for results computed on a single database, whatever you want to call it, a snapshot in time of the database. You'd like the statistics to be consistent.
But no matter when I do this, it's not like within one query that I sent there, but if you do this today and I do this like 3 months from now, it would still be consistent.
Well, I mean, we'll invoke our mechanisms on a single database, which represents a snapshot in time. And then I want this, which is a potentially large set of statistics about that database, to be internally consistent, in the sense that even though there's noise added to them, there exists a single database from which all of those workload queries could be derived.
So if I come in 3 months later, I get the gray box down there. Got it. Okay. Yeah.
Okay. So, there's lots of intuitions here. You can think of this as a kind of compilation procedure. If anybody has encountered experimental design, this is essentially a lot like an experimental design problem where you're trying to figure out an unseen vector x, and you've got some constraints on what you can measure about x. It's just sort of like unusual constraints that arise from privacy. Experimental design has been studied elsewhere. Okay, so there's been lots of work that can be viewed in this paradigm of select, measure, and reconstruct. And there's basically, it differs on like it was targeting certain types of workloads, maybe marginals or one-dimensional range queries. And these fixed methods are basically matched a strategy or a set of measurements that worked well for a fixed workload. Okay, so it's sort of like there's no hard optimization problem. It's just an observation that if you care about one-dimensional range queries, it's good to form trees of measurements, and then you can do reconstruction efficiently. Okay, so we'll come back to this. Or if you're doing two-dimensional range trees, you do two-dimensional quad tree type stuff. And then there's another, and then that grew into the matrix mechanism and other things that tried to solve an optimization problem that said, whatever subset of this class of workload queries is, I will try to solve for a good strategy. Okay, so I want to just walk through some of the intuition here, because for the workload that motivated our early work in this area, which was range queries, and we talked about this again, but I want to show you a slightly different example. So if you want to answer the set of all range queries, that workload has high sensitivity. There's a lot of queries about n squared over 2, where n is the domain size. And one measurement set you could clearly use is called the identity. I'll show you a picture of this. This just means measure each element of the unseen vector x and get a noisy estimate from that. And then you can derive, easily reconstruct answers to your range queries. Another work in this area observed that if you use measurements that are derived from a Haar wavelet, you get good performance on range queries. And people also tried tree-based things. So let me show you what these things look like. Now, this is a strategy matrix, and remember that the rows are each going to be measurements. Okay, so I'm going to multiply each row against my data vector, which is size 4. And so the identity matrix is saying, estimate the first component of the unseen data vector, then estimate the second one, and the third and the fourth. Okay, you get noisy estimates to each of those. Whereas this hierarchical thing, this is analogous to the tree that Sasha showed us, where the first measurement is really the sum of each of the components in the unseen vector. And then we kind of decompose and we sum the leftmost 2 and then the rightmost 2. And then we have the identity matrix as a sort of submatrix here. Okay? And the observation there is that you can reconstruct any range query from logarithmically many noisy estimates. Okay, because the problem is that the noise added to each of these measurements is independent, and when you use a lot of those estimates and sum them together, the variance accumulates. Now, this wavelet thing doesn't look much like a tree, but it has some similar aspects. It has the observation which sums all the elements, and then it kind of decomposes things in a binary way, but it's actually taking the difference between the right half and the left half, and then the difference between these two cells and these two cells. Okay, so so the art or the goal of choosing a strategy for your workload is, it should have low sensitivity. But if we just wanted low sensitivity, we would do this, because the sensitivity is the absolute column norm, all right, the maximum absolute column norm, right? These two strategies have higher sensitivity, but they support efficient reconstruction. And just to so this is what happens sort of empirically if you run these and you look at mean squared error, so higher error on the y-axis, and you look at the range queries, and I've organized them by the width of the query, okay, as a fraction of the domain size. And what you see is with identity, the larger the query, the larger the error. And that with these hierarchical techniques and wavelet, you're getting very similar performance. And what you do is you pay a price for the small queries. You would have done better for small queries if you had asked identity, because it has lower sensitivity. And small queries, you don't need to add too many things up, so the variance doesn't accumulate, right? But for the large queries, you would do very badly with identity, and this is sort of substantially dampened by these hierarchical techniques. So actually, the hierarchical technique was a paper that we wrote, and then somebody else, like almost at the same time, wrote this paper on wavelet, and they were both targeting differentially private answering of range queries. And we were really curious to understand how, I mean, we didn't have this graph, so they look almost identical in performance, and we were trying to understand, also the wavelet stuff, was actually described as a transformation, where you take your data vector, you transform it by a wavelet transformation, then you apply the Laplace mechanism and you transform things back. So it is a little bit of a different language, but really, it started us asking questions like, well, if these are two comparable approaches to range queries, sort of which one's better and are they optimal and stuff like that. And one interesting tidbit here is that if you take the wavelet measurement matrix, it turns out to be equivalent, exactly equivalent as a measurement matrix to this thing, okay? And which is interesting. But if you know a lot about differential privacy, especially epsilon differential privacy, and applying the Laplace mechanism, you see that what you have is sort of like redundant measurements. You've measured this cell twice. You usually get penalized for that under epsilon differential privacy for measuring, so asking the same query twice. You're better off actually asking that query once and adding some weight to it. Okay, so this actually has the same sort of like, it distributes error the same way, but the sensitivity is reduced. And so you can show that as a strategy for answering range queries, this little matrix is, dominates this one. All right, so just to show you that there's sort of subtleties here, and that there's nothing special about the wavelet matrix, and it's actually not optimal. So the question is like, what's optimal and can we find it? Okay, so that sort of motivated the matrix mechanism in our formulation of it, which is, which is the following one-liner, and I think it just makes sense to show you, compare it with this. So this is the Laplace mechanism applied to the workload. You multiply the workload matrix times the data vector, which is x, not h, remember. And then you take a vector of independent Laplace noise and scale this by the sensitivity in epsilon. Right, so that's the standard Laplace mechanism. This is a little bit different, but not so different if we look at it this way. These are the true answers to the workload queries. This is the noise transformed by this WA pseudo-inverse. Okay, so this is sort of like, and then scaled, but not by the sensitivity of the workload, by the sensitivity of the strategy matrix. So that's how we achieve some of the savings of reducing sensitivity of the strategy matrix. Okay, so this has closed form error. So there's an error expression, which given the workload and a strategy matrix, we can compute the error. And this is similar to what we saw before. This is the total squared error across the workload. And the data is not in here anywhere. Okay, so we know what error we're going to get for any database, and that's a nice feature. Okay, unfortunately, it's hard to find the optimal strategy in our formulation. It's got a lot of parameters. The pseudo-inverse is inexpensive to compute and not well behaved. The constraints are hard to encode, and it's really not smooth. Okay, so we were never able to solve this in practice, for anything. So it was interesting to study. There were attempts. I mean, we described in the original paper how you could solve this, that it was like an SDP with rank constraints. This is for the L1 case, or for epsilon differential privacy, and that you could put it into SDP form. But n here, little n is the domain size for us. It's the size of this vector. So even getting it into the form of a convex optimization problem, it's just still completely infeasible for interesting examples. Okay, so this is a simplification of an attempt to find a set of data cube queries that doesn't really compute the true error metric. And this is the low rank mechanism. So I'm not going to go into detail with these, but we're going to come back to this. So that's where we were with the data agnostic algorithms that are instances of this select, measure, reconstruct paradigm. Right? There are lots of examples from the applied literature. There are instances of that, all sort of implicitly doing this least squares reconstruction. So the second approach, which I'll mention briefly, and then come back to at the end, assuming I have time, does something a little bit different. So we've got the workload as input, and then I sort of describe this, try to put these things on the same footing by saying that there's some tests done, or some modeling of the data done as an initial stage, which is then used later to choose or influence the measurements that are taken. And then noise is added to those, and then maybe there's reconstruction. Okay, so this is like an extension of select, measure, and reconstruct, where and this whole thing could be iterated, but where we test or model the data set. Now, the intuitions that are embodied in this class of mechanisms are that there are some times or situations where we know that we shouldn't try to measure something. And that's a data-dependent thing. And if we can detect that, and we might have to do so privately, so use some of our privacy budget to detect that, then we shouldn't measure those things. Okay, so in the multiplicative weights exponential mechanism algorithm, I guess you could say that the sort of like inspiration is that don't measure stuff you already know, or your current estimate is good enough for this query, so don't spend more of your privacy budget learning more about the answer to that query. There's some other techniques that try to learn something like, so another thing that we sort of informally know is that at certain epsilons, you're not going to be able to really differentiate sort of like small counts from one another, or small differences in counts from one another. So you sort of shouldn't try. Another thing that these algorithms do is often they will try to detect regions in the domain. If this is like a one-dimensional histogram, they might try to say, you know what, actually, this region looks pretty uniform. And I could approximate it well by just assuming uniformity. So if I can detect that ahead of time, I won't try to measure the individual components here or range queries in this region. I will simply measure the total sum of all of these buckets and then stop measuring things within that region. And you can you can lower the variance substantially by techniques like that, but you introduce bias. Okay. Oh, and also I want to point out, I talked to Marco about this, so I wouldn't feel too bad. But dual query is an algorithm that doesn't really fit well into this set of categories. So I sort of like am not doing it justice. We may come back to that at the end. Okay, so there's a number of applied works that are embodying these principles of sort of like testing something about the data that will then influence the measurements taken and then maybe do some reconstruction. So this is the multiplicative weights algorithm. These algorithms are, for the most part, doing types of things where they detect how large the counts are, and they sort of like, they tree structured things, but where you cut off the bottom of the tree when the counts are too small because you sort of realize that you can't, you don't have enough signal to make measurements worth taking. This technique is similar to like finding regions that are well approximated by uniformity, and then you could think of this as modeling the data, imposing a model on the data which says this region is assumed uniform and this region is assumed uniform. This technique privately learns the structure of a Bayes net that would fit the data well, and then in a subsequent step measures the statistics that underlie the Bayes net, and then does some reconstruction. And then there's dual query, which I guess you could say, chooses, tries to measure minimum payoff records or something like that. Okay, so if we try to compare these, in the data agnostic world, a lot of things look like select, measure, reconstruct, and although there are different ways to reconstruct, to me, they seem sort of like it's a more orderly set of techniques, whereas in the data adaptive world, there's more variety. One really nice feature of data agnostic techniques that I've mentioned is that the workload query error is easily computable in most cases, and it's non-sensitive. So we can release the answers to the workload queries and closed-form estimates of error. And whereas with the data adaptive techniques, oftentimes we can't compute the error readily. We can't predict it because it depends on the data. So so we would have to use some of our privacy budget to release error bounds, and then those expected error rates would be themselves noisy. And so in practice, this can cause some challenges. So in the data agnostic world, also we have unbiased query answers, which is to say that the expected value that we get out for our workload query answers equals the true answer, whereas that's not true for many of the data adaptive techniques. And that's also a problem in practice because we have systematically biased outputs coming out of some of these algorithms. Our empirical study that I'll get to a little of this at the end of the talk if we have time shows what Sasho hinted at, that if you have a lot of signal, meaning you've been granted a high privacy budget or you have a lot of data, then the data agnostic techniques tend to outperform. Whereas if you have very low signal, a little data, not very much data, or small epsilons, the data adaptive techniques tend to outperform. At least that's true in low dimensional settings, and we haven't studied the high dimensional settings as rigorously yet. Now, both of these approaches have scalability challenges. The biggest one in the data agnostic setting is this reliance on sort of materializing the data vector, which is exponential in the domain sizes or the product of the domain sizes of the attributes. And so it can really break down for high dimensional data. And there are also scalability. So it's a little bit of a mixed picture with the data adaptive mechanisms. Some of them that are trying to model the data, privately model the data, some of these techniques really don't scale very well, especially for large data vectors. But then we also have things like dual query and the priv Bayes algorithm, learning the Bayes net, that really do scale well. So it's not sort of uniform. Okay, so any questions about this? And I'll transition to the census example at this point. Yeah. Okay. All right, so I want to, I'm going to kind of stay in the data agnostic select, measure, reconstruct paradigm and talk about the census example, which is sort of a live challenge that we're facing. So the census, as many of you know, is testing differentially private algorithms for release of some of their key statistics coming out of the 2020 census. And summary file 1 is one of their major data products. it describes persons, that is people, but they're called persons at the census, and how they are grouped into households, which are just groups of persons with a head of household and usually kids and extended family. We're not going to talk about households. Households are a little bit complicated. We're going to talk about queries over persons and keep things simple. And I'm going to refer to summary file 1 as SF1. And the schema for this data looks something like this. So we have sex, male and female, relation, which is the relationship that you have to the householder. You could be the householder itself, or you could be sibling or child or parent or something like that. Ages from 1 to 115. So there's 17 different relationships to householder you could have. Race and ethnicity, which there's 63 different race combinations because you can be more than one, you can be multiple races. There's like 6 race categories, but you can be any permutation of, you can be all 6 or any subset of those. And then you can be Hispanic or not Hispanic. So that works out to 126 different race ethnicity combinations. So these are what I refer to as sort of the demographic properties. Those are composed with geographic. So we can measure how many people are 115 years old and male at a number of levels of geography. We could ask that in the whole nation, or we could ask that at a state level or a census tract or a census block, which is the smallest, sort of roughly equivalent to a city block. And there's like 11 million of those. So now we think, this is where the data, the whole notion of turning a relational representation of data into a vector representation or in a histogram starts to really break down. Okay, so I have the domain sizes on the next slide, but this 700-page document, which you can read, it's freely available online, describes exactly the tabulations that are made public. They're called tables, which I hate because I'm a database guy. They're not tables there. I guess they're contingency tables is sort of what they are. They're like a weird form of contingency table. And if you just look at the more basic, there's more than 4,151 counting queries if you include household stuff. But if you just look at the ones that talk about persons, there's about 4,000 of those. And that's a workload. Okay, so that's actually a very nicely encoded, except that it's a PDF document and there's 700 pages that you have to read. It's precise and it's a workload, just like of predicate queries. It's exactly.
So we don't have to.
Right, I read.
What do you mean it's a weird form of a contingency table?
I guess what I mean is that there's some ways in which it's nested that I think are not standard for contingency tables. But contingency tables is not. It's not my home domain, I have to admit.
Contingency tables, typically they're just, you would take all these variables and let's say they were treating them all as categorical. So I forgot how many you listed there, like 8 or something like that. And basically you would say the product of all 8 of them and you would get like billion cells. And that would be one massive contingency table.
That would be a massive one, but you could imagine one that only looked at a few of the variables.
But you can take only 3 of the variables, cross-classify, and record the number of individuals in each of these tables, and that's a typical contingency table, right?
Exactly.
But there's no hierarchy in there of any sort. And I think in some of these tables, and maybe Frauke knows this better, there are many different tables they produce, right? And some of these tables have certain associations and hierarchy embedded in them, so it's not a continuous.
If you got rid of like the states and tracts, which have a hierarchical relationship.
Yeah.
Well, but so.
Because of like the states and tracts, right? If you got rid of states and tracts, it would basically be.
So let me come back to this because in a few minutes I'll describe a structure for this workload, and I think it'll become clear what's a little bit odd about it. So if we just look at the demographic properties, the domain size here is about 500,000. Okay, and we sometimes say this is we've ignored geography or we've like aggregated up to the national level. Okay, and if we want to extend down, we can get much larger domain sizes or histogram sizes. We would have 25 million values if we just did all of these demographic possibilities times the 52 states, and then we get a histogram this size if we include full geography. Okay, all right. So now we think about. Like, okay, let's run the matrix mechanism, except that the SDP we have to solve is over a workload matrix with the number of columns equal to 25 million, and so we're in trouble. The nice thing is,
are there structural zeros at the person level?
yes, there are.
And then
Yeah. Oh, that you could omit and shrink this? Yes, and that's something that the question was, are there structural zeros at the person level? And so there are things like people who are age 5 should not be grandparents. And so they shouldn't have a relationship to householder, which is grandparent. And you should definitely have a 0 for all of the, at every level of geography, So there are things like that. And they're trying that, but it's, I don't think it's going to dramatically change the dynamics of the problem. Okay, so what I want to describe is the structure in these workloads. So I'm going to define a product workload as a kind of like cross product of these Boolean conditions on attributes. So if I describe a kind of sub workload on age, which is saying I have one condition which is age greater than 18. They don't have to be independent, but age equal to 65, age in this range. And then I have some other conditions on race, and I take the cross product of these. I will put the conditions, I'll pair the conditions together in all possible ways and conjunct them. Okay? And this allows me to, this is exactly what's happening with marginals. So you should think of this workload, the census workload, as like a generalization of marginals. Marginals are product workloads where the sets of conditions are either the identity, meaning that it's an enumeration of every domain element for age 1 through 115, or it's just totaling, like marginalizing out over the attribute and saying, I don't care what your relationship is, and I'm going to aggregate over it. Okay, so this is a two-way marginal as a product workload on age and race. This is one of the tables where it has this nested structure where that asks for the total population. Actually, every table contains the total population, and then how many males there are, and then break down the males by those that are under 5, 5 to 9, 10 to 14, and so on. Okay, so that's this table P12 written as a product. All right. So product workloads can encode the Cartesian product of counting queries. So all multi-dimensional range queries, a single marginal or maybe all marginals. And if we might need to encode, we might want to encode a workload that's just a union, a combination of multiple product workloads. We just say that's a union of products. Okay? So that could be arbitrary collections of multi-dimensional range queries, collections of marginals, or the SF1 file, which can be encoded as the union of 32 product workloads. There's other ways to encode it. The sensitivity turns out to be 50. Now, I'm almost done. I have 2 more slides before the suspenseful break that we'll take. So this is not a complete enumeration, but this is sort of like some of the tables expressed as products. So this is like identity on sex with some coarse age ranges, and then marginalizing out race and ethnicity and relationship. And if we include geography, we go to the block level. Okay? Now this is then there's a table that's like only cares about under 20 people of both sexes. Race and ethnicity and relationship doesn't matter at the block level. Okay? And then something else at the track level. Now this one is important. Notice that this says, doesn't care about sex, cares about race and ethnicity, and this is race combinations. This is like all the enumeration of all possible races plus these weird conditions on like, are you 2 or more races? Are you 3 or more races? It aggregates those things. And then it only cares about whether you're over 18. Doesn't care about what, anybody have a hint at why this is an important tabulation?
Voters.
Voting. They're counting the ethnicity of voting age persons, which is really important for redistricting because it's the basis of the redistricting data. There's a special law that governs this. It's given out at special times, and it's important that it be accurate. Okay? That's a little foreshadowing because I want to eventually raise the question of if this is the whole workload, but this product workload, this particular product is really important, we might need to weight it or something. We might want to devote more of our privacy budget to it or something like that. Okay, but we could do that if we could run the matrix mechanism, because we could weight things, but there's a problem. These objects are really big. So this was the matrix mechanism in sort of algorithmic form, where we have to look at the steps and when things break down. So this is the census table that we would take in, and we would vectorize it to get our data vector. The problem is the data vector is big. Even at the national level, it's we said 500,000. At the state level, 10 to the 7th. Okay, so it's getting really big. So we're worried. Then we have to materialize our workload matrix, because that's what we're going to feed into the optimization problem. Oh boy, because then we have 4,000 queries times the domain size. So at the national level, that's an 8 GB matrix. At the state level, it's 22 terabytes. All right, and this is the thing that Sasho wants you to run an SDP on. Sorry to single you out. So then we have to solve the optimization problem. And then we should also not forget that we have to do reconstruction, which might involve a pseudo-inverse of this measurement matrix or something and that could also be a problem. So the suspenseful question is, how could we ever run this algorithm at this scale? Can we? Will we be able to? You got to come back after the coffee break.